Hello, everyone. Yes, so I think we are just in time to start this last session of the school. We have the pleasure to present to Chris Fryer from Los Alamos National Laboratory, and he will talk about the potential advances in transient studies of under two proposed NASA missions, SIBEX and Gamow. So go ahead, Chris, and you have 40 minutes.
So I assume you can see my slides. Do they look okay? Is it in the full view there?
Yes, it's we can see you in bigger screen, so it's okay.
Okay, so I'm. This is kind of a haphazard talk. We're going to talk about a few different topics, and it's more because I want to get your insight, feedback, comments on any of these. But I wanted to talk about two. NASA has gotten interested in time domain and multi-messenger astronomy, and so they're working on a lot of, they convinced a lot of people to propose new medium explorer missions, and I want to talk about two of them that I know that have gone on the current round. We'll know probably at the end of August what missions are getting selected for the Phase A studies. So definitely both these missions will not get selected. I'm hoping that one of them will, because they both do very interesting science. And I'm going to talk about some of the science that these two missions are doing. And they're tackling different issues in supernova and gamma ray bursts. So I thought I would go over some of these issues in I'll start with supernova and then talk about some gamma ray burst aspects of these missions in my talk. So let me start with supernova. For those of you that don't know, that we now have a standard paradigm for most supernova, or what I would call normal supernova, where we believe what happens is that you have a massive star. It goes through those subsequent series of burning phases until you have an iron core in the center. That iron core keeps on going through silicon shell burning until it gets so massive that it compresses enough that the electrons in the core start to capture onto protons. And that iron core was supported by thermal pressure and electron degeneracy pressure. When you start to capture electrons, you remove that pressure, and so it compresses further. The electron capture rate goes faster. You start to dissociate the iron core into alpha particles, and it does this runaway collapse bounce phase. That was our model in the 1980s, but we realized that wasn't all the physics we needed. And the kind of new physics of the last 2 decades that people have been pursuing is you have that material collapses. It collapses down until it gets to neutron density, so densities of around 10 to 14 grams per centimeter cubed. And at these high densities, neutron degeneracy pressure halts the collapse. It causes a bounce. The bounce doesn't explode itself, but it leaves behind a region that is convectively unstable. And so in 1994, Mark Herant did a series of calculations where he found that if he modeled that convection, he could more easily take the energy from this bounce. So you released a whole bunch of 10 to the 53 ergs of energy when you collapse from an iron core down to a neutron star. He could take a fraction of that, was better at taking that energy that was released, that potential energy that was released, that went into thermal energy and neutrinos, and extract it and drive an explosion. So you have this convective engine region where you have, at the very center here, you can see it in my slide, you see this hot protoneutron star. You have this region where, and the colors on this plot are entropy, and the vectors are the velocity. So you have material raining down on this bounced core. So the rest of the star is just realizing that its core has collapsed on itself. So it's falling in onto that collapsed bounced core. And you have this region where high entropy material is moving upward and low entropy material is down flowing inward. And this is a slice of a 3D calculation that Mike Warren and I did in 2002. But this kind of picture is what we get for that convection. So you have this kind of lowish mode convection. The convection is able to take the energy from the neutrinos leaking out of the protoneutron star and convert it into kinetic energy, pushing against the infalling star. If it can blow off that infalling star, you have an explosion. And so we're now, almost every group in the world, when they do this kind of physics well, they get explosions. We still disagree on the nature of the convection. We disagree on the nature. We get different answers for the amount of energy in the explosion, and that looks like it depends on the details of the neutrino physics, details of the equation of state, details of magnetic fields, all of this kind of physics that we have to include, details on what the exact nature of the star looks like before you collapse. So there's a lot of work to be done. Yes, go ahead.
And the rotation, maybe.
Yes, and the rotation. This is a non-rotating star here, but the rotation will affect it as well. So there's a lot of physics that will affect the answer, but this basic model explains the mixing that we had seen, the outward mixing we had seen in Supernova 1987A of the nickel 56 and the iron. It explains why the supernova energies are typically at the 10 to the 51 erg level and not much higher. It explains we seem to be fitting the progenitor masses, and we're looking at the remnants, supernova remnants now, and I'll show some results on that in a little bit. But a lot of questions remain, and I discussed them that we're still trying to understand. And this isn't the only way to make a massive star explode. And the question is, these alternate mechanisms for stellar explosions, how prevalent are they? Are they, I think for weird supernova like hypernova, this is not the engine. It's not the only kind of explosion you'll see, but it is the explosion for a lot of the run-of-the-mill supernova. And we kind of, showing how the different models have come in favor and disfavor has a lot to do with the observations. For the longest time, this is an image of the Cassiopeia A supernova remnant, and initially the green data here is the silicon, so it's colored by what are the dominant lines. So the green is silicon, red is iron, and the green and red are material that was shock heated as the supernova plowed through the interstellar medium. A reverse shock goes through that material, and you see the shock heated material, and you see these features. And the remnant community has used this to try to predict what the explosion is. And for the longest time, the remnant community wanted this to be a jet because the silicon had this jet-like feature toward it. The problem is the iron didn't follow that jet. And there's a lot of, in these, when you're looking at a remnant, it's not just affected by what the explosion is, it's affected also by the surrounding interstellar medium. So if you had any weird stellar effects before the supernova explosion, that would affect what the remnant looks like. So NuSTAR, the satellite NuSTAR, decided, let's try to solve this problem. Let's look at an isotope that's produced down near the engine, and titanium-44 is produced down right near the supernova engine. And that if you're looking at a radioactive isotope, you don't need it to be shock heated to see it. You're just seeing decay lines from that radioactive isotope as it decays. And so in titanium-44, I don't have the problem of what is the circumstellar medium doing to my shock. This is just what the engine looks like. And what we ended up getting was this clumpy ejecta, which really is only fit by an engine, this kind of convective engine. Of the proposed engines for supernova, this kind of clumpiness was actually predicted by our convective engine. It's these different lobes moving outward, and a lot of modelers, including Thomas Young's group in Max Planck in Garking have produced models that fit well to this kind of observation. So this new star observations were kind of what sealed our understanding of this mixing probably is coming from this mixing in the engine. We had a lot of other data from 1987A where somehow we had to mix the material out. But I think with this new star observation, we're starting to understand what's going on here. We still don't understand what the iron is doing and what the unshocked iron is doing. And Danny Milicevic has got some time on JWST to look at the unshocked material, and that will, when we look at the unshocked iron, I think that will give us a really good idea of what's going on in this explosion. So, I mean, there's still details to be fleshed out, but and those observations will hopefully happen later in the summer. So that's our picture for the engine. How can we get that from, it's hard to get. We only have one cassette that's close enough to get good data. We only have one supernova where we have neutrino observations. How do we get more data to try to, or find new diagnostics to try and constrain this asymmetry? And one of the things that we've been looking at is shock breakout. Shock breakout is the emission that happens when, and I assume when you had the Ultrasat talk, you had some details on this. Shock breakout happens when the explosion first emerges out of the star, and when it first does that, you get a burst of photons in the X-ray and the UV that can probe the asymmetries in the explosion. Unfortunately, it also is already starting to get mucked up by other asymmetries. So the shock is moving outward. It is asymmetric itself. So this red curve here is my supernova shock, and it's moving through stellar convective regions. So this is a star in the convective regions of the star. That will produce more asymmetries. And then the shock moves through winds or the circumstellar medium, and that has other asymmetries. And all of these will contribute to what we used to call shock breakout. I like to call it shock emergence or something like this, because it's not just a breakout of the star, there's other shocks going on. And there's groups in Santa Barbara doing the shock moving through the convective region, groups in Israel looking at asymmetric supernova blast waves moving out. So Chris Irwin has been leading that. So there's been a lot of studies now of these features that what we're doing. What we have done at LANL has looked at as the shock goes through these asymmetries in the circumstellar medium, and here we just studied some clumps of the shock moving through the interstellar medium. The plot on the bottom is showing that we get additional shocks that heat up the material, produce more X-rays, produce more UV, and we have to understand all of this physics if we're going to understand the shock emergence emission. And the plot on the right here is just showing you what it looks like when the shock moves out. It accelerates as it moves down that density gradient. You can get that if you just look at a simple set-off solution. And then it decelerates as it moves through the wind. And it's the shocks that are produced there that are part of what we see when we observe these shock breakout emissions. Any questions? So it turns out that the shock heating also is driving what we're seeing in the supernova light curve. So it's not just the early shock emergence that we care about it. Nathan Smith at ASU has been looking at a lot of, this kind of shock breakout emission not shock breakout, the effect of these shocks on the later time light curves. And one of the things you would have to worry about is we know that most massive stars are in binaries. They go through things like common envelope phases that eject mass. And this is just a simulation by Jean-Claude Passy, where he looked at the outflows and how that can affect the mass loss. And that is one of the things that we're looking at with Nathan Smith to look at how does this affect the light curve. But there's a lot of other effects that affect the light curve. And I wanted to remind, we had Laura's talk yesterday, but if you have a supernova go off and it's in a close binary, that's also going to affect what the ejecta looks like, and it's going to affect the light curve. So this is an important, the stuff that Laura was studying is important for this gamma ray burst model, but in models that say they're slightly different, don't get the accretion needed to make a gamma ray burst, you can still get conditions where you're affecting the light curve. So I think the conditions that Laura is modeling are not just important for gamma ray bursts, but I think there's probably a sizable fraction of supernova that these kinds of conditions will also affect. So all the circumstellar medium things that we're studying, mass outflow from winds, explosive winds, common envelope events, and supernova in binaries, where the compact binary is affecting the outflow. All of this is going to affect what we see in light curves. I think so. These studies are not just important for gamma ray bursts. I think there's probably a whole slew of supernova that are affected by these studies. So one of the things that I want to work with Laura on more detail is looking at a broader set of systems that maybe don't produce gamma ray bursts, but could produce weird supernova or effects of supernova that we're seeing. And so I think there's a lot of interesting results there. To tie this into physics, go ahead.
And especially in this house, we are looking at the limit, and we will send you a paper which we are working on today about the limit of BDHN1, where the system is a single star, and there are beautiful results coming out from the cocoon, which we are trying to interpret within our framework. This looks very, very, very exciting, although in the limit of a single star, not in the binary. But it's a continuous. But the advantage of the cocoon is that they are very, very beautiful data from Itzo and other people, which we are looking at. We are preparing a paper and send to you.
Yeah, I think there's a whole bunch of work, so we can take some of this data and do the supernova light curves in gory detail, and I think we're going to see there's a lot of interesting effects happening. And so I think yes, please send me the paper and we can discuss it in more detail. One of the things that I wanted to tie this all together in is this kind of, this shock interaction, clumpy medium, having stuff run into clumpy medium and studying the shocks. It's not just interesting to us in astrophysical transients. The national labs are interested in it as well. And this is an experiment. I wanted to show you that we're actually studying this physics on the micro scale. This is an experiment that we're running at Los Alamos. It's being done at there's in Rochester Institute of Technology. There's an Omega laser. So we have a Omega laser is used to heat up a hole that drives a radiation front. So here's our hole on this plot on the left. We have a hole, and then we have a target that the hole heats up and drives a radiation front through the target. And then we're simulating this target and modeling we put in some inhomogeneities in the target, and we're modeling the effects and the physics and the shocks that happen as the radiation flows through the target. So it is actually not so different than the wind models I showed here, where you have material going through this clumpy wind material. Now I have a laboratory experiment where I'm running a radiation front through a clumpy material. The only difference is the size scale. So whereas I was looking at a Wolf-Rayet wind, 10 to the 11, 10 to 12 centimeters in size, this is a target that the entire target is 1 centimeter in size. So the extent of this region is 1 centimeter. And I show you the density, the temperature, and the composition as the shock is moving through. And what happens is we're seeing the physics that you'd expect to see. The radiation front goes through, it heats up the clumps, they drive flows that drive shocks, and that's that shock heating that we're seeing, that we believe we're seeing in these shock emergence observations that have happened. So we're doing simulations of we're checking our simulations against laboratory experiments. And then we're also comparing to the existing data of what we know about shock emergence at this time. And right now there isn't a lot of data. So probably the best studied object is Supernova 2008D. It was discovered by chance with SWIFT. Elisa Soderberg was looking at something else, and 2008D went off, and she got really nice observations of the shock breakout. The timescales are usually short. The other kind of data we have is later time data, days after the explosion, the initial breakout in the ultraviolet. And the bottom two images here are showing, all of these images are showing models of our shock breakout events where we put in different clumpy media. And so if we don't have very many clumps, the image on the bottom left, most of our shock breakout or shock emergence images dim down very quickly, and we don't see them after a few days, or they only explain the dimmest of the observations that Swift UV has done. But if we have more shock interactions, and the image on the right, we see that we match those red dots. So all the dots are different supernova that were observed by Swift. And we see that data, if we have a lot more shock interactions, we can explain the later time UV observations. But these are the initial shock emergence. These are after the supernova has gone off, and we're looking at late time shock interactions. We do have hints of data from other missions. So Alpen Larsen looked at XMM data and found a set of potential candidates where they saw X-ray emission at early times at these essentially in the first day in X-ray bursts that we think may be this shock breakout emission. And the interesting thing is the simple models of shock breakout did not predict strong X-ray in red supergiants, but Alpen Larsen see it in the red supergiants. And this is because the simple models didn't include the physics of a lot of the shock interactions. They just did the simple shock accelerating down the edge of the star as you go from the edge of the star to the wind. But they didn't have all this clumpy medium studies that we now know will affect the light curves. And I think the Alpen Larsen data are showing that detailed physics must be included to match the data. Ultrasat is going to go up. It's a wide field UV satellite that will detect the UV emission. But the mission that I want to talk about is SIBEX, and it's so the emission from the early shock emergence comes out in the UV and the X-ray. Ultrasat will get to UV, and this is a good first step. SIBEX is, it looks like my connection. I hope you can still hear me, but it looks like my connection dropped.
We can listen. No, we can listen you very well, Chris. Don't worry.
Very well, perfect.
Okay. Hopefully my connection gets back because I'm not sure you'll see my slides when I advance them. But what I want to talk about is the SIBEX mission, which is essentially Ultrasat.
I think we lost your slides now.
Yeah, so I just advanced. I'm hoping that in the it says it's trying to connect. So I'm gonna hopefully I'll connect.
Chris, may I ask you something in the meantime?
Yes, go ahead.
Yes, about this picture that you showed before. So is that related to our idea of 2016? You remember when we made this model for the supernova 2006 AJ about the shock going through different mass columns because of the asymmetries of this in the binary, and so causing different emissions at different times. Was maybe that the main idea also in this case?
I think you are muted, Chris. I don't know if it's a problem of connection or.
How about now? Can you hear me now?
Yeah, we can hear you now. Yes. So did
okay,
you?
And I'm going back to sharing my screen. Let's see if. Do you see my screen now?
Yes.
Okay. So in answer to your question, so there's a lot of effects that we worry about. So it's the binary effects. I mean, the problem is there's a lot of effects. So the images I was showing were just, when we're trying to do these shock explanations, I had just artificially put in, I know there's some material that the shocks are running into that are driving extra emission, but there's lots of different ways to drive extra emission. And I think this is the hard part, is we have to study all of them to get all the shocks that happen. It's a really complex picture. And so the ultrasat will get us some hints on how important this is, but I think in the end we're going to need something that has a lot more data, and that's where the SIBEX mission comes in. So do you guys see my SIBEX slide? There should be a picture of SIBEX on the right, and
Yes.
characteristics of the SIBEX mission. Okay. So SIBEX is it's a X-ray plus UV, gets spectra, both X-ray spectra and UV spectra. There's a typo here. It's 0.1 to 10 keV in the X-ray with about 100 eV energy resolution, 0.3 stereo field of view. The UV spectrometer goes from 130 to 300 nanometers with about 1 to 3 nanometer resolution with a much smaller field of view. So whereas ultrasat is a really wide UV instrument, the goal of SIBEX is to detect the shock emergence in the X-ray and then slew the UV instrument to get the UV spectra. The strength that SIBEX has is it gets the emission is usually in the X-ray and the UV, so it'll cover the full broad emission from this from the shock breakout and the shock interactions, and it also gets spectra, so we can do things like in the X-ray, it's more getting the profile of there's fewer lines. There's some lines in the X-ray, so we get some lines, and we'll also get the kind of a temperature estimate. And the UV, we can get a lot of the lines that we're expecting to see in the ultraviolet. So this really gives us a complete picture of this complex event that we will be able to see the shock breakout in. And we went and looked and said, okay, how many will we detect if SIBEX gets launched? And instead of having a handful of supernova, we'll get up in the course of the lifetime of SIBEX over 1,000 shock breakout events. So we'll go from a handful to something where we have detailed information about thousands. And the different models here are different shock breakout models that we've been using to compare to the data. So now I want to go from, I was talking about supernova, I want to go over to gamma ray bursts. And SIBEX will also study gamma ray bursts, and the focus it has is on, because multi-messenger is such a hot topic right now, we're going to look at events that are nearby detected by gravitational wave detections. And one of the things that people don't understand is when you look at these, we're excited, kilonova produced, and I've heard people say it, GW 1708-17 produced 0.04 solar masses of our process yield. The real answer there is that we know that GW 1708-17 produced somewhere between 1,000th and a 10th of a solar mass of heavy R process. We just don't know from the limited data we have. We need to get, there's lots of uncertainties in calculating the light curves. What's the exact composition? What's the density profile? So there's so many things that affect the determination of the composition that we need really detailed data to really constrain what are the ejecta masses in the R process. And so one of the things SIBEX will provide is early time UV spectra of these gamma ray bursts. And these different spectra here, so I'm showing spectra between 130 and 300 nanometers. These different spectra are the spectra produced by varying things like the uranium composition or the density profile. So they're different of the ejecta. So the ejecta, we know that it ejects a certain amount of material. If you look at most people's light curves, they've assumed a canonical velocity versus mass distribution, actually that came from the 1A community. And so that it made an assumption for that distribution. If you vary that distribution, you get very different spectra. So, we're going to need this kind of ultraviolet data to help study gamma ray bursts. And this, I kind of drive that home. Did Nora talk about GRB 211211A? Or has anybody talked about that yet?
Laura, are you there?
Yes.
Yeah.
No, I didn't talk about that.
Which number?
Okay, so this is GRB 211211A. And so the reason I'm talking about this event is it's a weird event, and I wanted to get your guys' thoughts on it. So I wanted to just go over it. Here's where the event occurred. It looks like it's offset from its host galaxy. So that suggests something that required a binary that gave it a kick or something. So we were thinking it was a neutron star merger, but then it was a long duration burst. Or if you look at it classically, the duration was more on the order of 20 seconds, 20, 30 seconds, depending on how you suggest it. It had some other peculiarities as you look at the variability, minimum variability timescale. It's kind of a little bit strange. And so it was off the normal events, but it is normally we would have classified this as a long burst, and we would have said, oh, it must be explained by a collapson. However, we saw the event, we removed the afterglow emission, and there was a emission coming out at the less than 1 day time scale that looked like a kilonova. In fact, the data is plotted here, and our kilonova models, we have a suite of kilonova models, and the kilonova models are plotted on top. And it seems this is just the excess beyond the afterglow, and it appears that this excess is fit well by a kilonova, and we tried to match it with other models like a low nickel 56 yield collapsar supernova, and so that's what we got fitting there. Although we could fit the ultraviolet with it, we could not fit the I and K bands with it, and so we also tried to fit it with a magnetar model, and the magnetar model didn't fit well the early time ultraviolet. So we did a lot of studies. One of the things I would love to do is, what about the BDHN model? Can we, would it fit this event? Because this might be a better, this would be a better explanation than some kind of neutron star merger that produces a 20-second long gamma ray burst. So I'll put it here. It's an interesting object. Hopefully you guys will think about it. There's a couple of papers already on the preprint server on it, and there will be they're all getting submitted to Nature, so there's going to be a series of Nature articles on this event. So anyhow, that's one where, and here we use the ultraviolet from SIBEX to help distinguish and remove. It allowed us to kill the magnetar model. So we can use this extra data from the ultraviolet. Really was important in helping us remove some of these models. And so I think SIBEX, that will do a much better job than Swift on this, will really help us constrain these models. And so I'm on the topic of gamma ray bursts, and I think another interesting set of gamma ray bursts that I think we'll learn a lot from is these high redshift gamma ray bursts. So I'll transition to the last topic that I wanted to give in my talk, and that is this Gamow satellite. So Gamow is a high redshift. Its goal is to look for high redshift, long duration gamma ray bursts. It has a X-ray telescope, not so different than the SIBEX Mission, 0.5 to 5 keV for its X-rays. Wide field of view, a little bit wider than I think it's a little bit wider than the SIBEX Mission, but it allows them to detect high redshift gamma ray bursts. Then they follow it up with an infrared telescope that will then allow us to get things like redshift estimates. So that's the basic mission. the kind of science case that we have right now for it is, look, we know how gamma ray bursts, if we assume that gamma ray bursts are produced by massive stars, we know what affects massive stars as you go to higher redshift. The primary metallicity effect is through mass loss, so that affects the evolution of the gamma ray bursts below a redshift of 1 or 2. But then you start looking at, so what you're really probing with high redshift gamma ray bursts in this, assuming a collapsar model, is things like the initial mass function or the binarity of these stars. And so this plot on the right is, here's the redshift on the x-axis, the fraction of gamma ray bursts versus the fraction of supernova, depending on the effect of if the initial mass function changes or if the binarity changes. And the kind of cyan curve here is what fits what Giancarlo Ghirlanda predicts right now from the observations. And so it's a kind of modest ion mass evolution with redshift. So that's what we kind of expect as a standard model if the collapsar model is the right progenitor. And so we've been looking at that. We can then predict a rate, and depending on the exact details of the model, Gamow will see either above a redshift of 8, 3 GRBs per year, or 0. And so we'll know, we'll already be able to constrain the initial mass function just based on, if we can assume that the collapsar model is correct, just on how many GRBs does Gamow detect above a redshift of 8. We'll get a lot of, we'll get probably a larger set of bursts above 6 and start to fill in that database of high redshift GRBs. So Gamow is going to get more high redshift GRBs. Nick White is the PI on the mission, and so if we can make these predictions. The problem is we've assumed a progenitor, right? We've assumed that the collapsar progenitor is what's producing it, and this is what the models are. Imagine that it's some different progenitor. We're going to have to use a lot of different diagnostics to help us constrain this. So if I do assume that it's a collapsar progenitor, I can also make predictions on what is the related supernova associated with it, what is the production of ionizing photons, so we can compare that to ionization fractions and results from JWST, and we can also look at element production. So there's, I can look at this and study this if I assume that the model is a collapsar. What we really need to do, and we haven't done yet, is what about other models for GRBs? So this is another topic I would like to talk to you guys about, because we should be studying this with different scenarios like the BDHN scenario, and say, what does it predict? Well, how does it affect these observables? And then we can start to constrain and get distinguishing features between populations of collapsars or BDHN.
I think we are ready to give you some input on that in the next week.
Okay, that's excellent. Okay, so this is, I think this is, I kind of did this talk in a way of getting topics that I wanted to bring up and say, here, we should talk about this more to get us going on some discussions. And so that's all I really wanted to cover. There's 2 missions being proposed. We need a lot of we need a broad set of diagnostics, and I think finally the U.S. is getting that for time domain astronomy is exciting. Multi-messenger astronomy is exciting. NASA is going to make this a bigger thrust, so there will be more NASA missions being planned for this. There's already some missions that are being proposed and are funded, like Ultrasat. I didn't talk about COSY, but COSY is a gamma ray mission that is more for imaging, but it might provide some nice information for us. So it's looking at radioactive isotopes. It'll be like NuSTAR Plus, so we'll get some interesting information from COSY. But here in this talk, I discussed 2 NASA missions that are being proposed. Like I said, we'll know at the end of the summer whether they're going forward. One of them was the SIBEX UV plus X-ray time domain satellite, and the other is Gamow. And it'll do shock breakout and core collapse supernova, so look at asymmetries in supernova and also neutron star mergers. And Gamow is an X-ray plus IR mission that will help focus on high-Z GRBs. And with that, I'll stop my talk.
Okay, thanks a lot, Chris, for this very interesting talk. And well, we have enough time for plenty of time, but for question and comments. So go ahead. Let's see if we have some raised hand.
Well, of course, one of the greatest news that we are following is the early phase, the UP data in the MEV, and I was planning to speak to Nick White to see if he can have a higher resolution of the UP data in the first 2 or 3 seconds. And we are going to come back to this ourselves in the next days or so. And we are discussing this now with Raim Moradi, who is listening, and of course with Jorge.
Yes, may I ask a question to Chris?
Yes, we have a question of Jorge and then Maria. So go ahead.
Chris, very nice, this idea of following the X-rays together with the UV, because maybe you, of course, you remember this double peak structure shows the gamma ray bar, the supernova associated with GRBs, this double peak structure in the blue band and the UV. That actually we show that injection of energy, for example, from accretion, from fullback accretion or from the companion star could actually explain those features. So I would like to ask you if you have some news about the study of double peak structure of supernovae.
Yeah, so here's the problem is you can get, for supernova, there are a lot of really bizarre supernova features that we want to try to explain in normal supernova. In these gamma ray, in the gamma ray burst plus supernova thing, you can imagine there's different, different processes dominate. But I think we also need to be looking at how does, material accreting on the neutron star after you've launched your supernova explosion, how does that affect the light curve? So there's other energy sources. So people, if you look at superluminous supernova, people have 2 models. They have either shock interactions where you're extracting some more of the kinetic energy of the supernova as it shocks against this inhomogeneous circumstellar medium, and you make supernova that way. You can also make superluminous supernova by, the favorite is always a magnetar, but I think you can also make it by accretion onto a neutron star or so many other effects. And that's why I get excited by things like, it's not just the accretion driving an outflow. If you have a supernova going off and then you have, but it's in a tight binary where the envelope quickly goes around, the ejecta goes around the binary, and that binary is affecting the outflow, that's going to affect the light curve as well. So it's both, you have more energy sources like accretion, you have shocks produced because you're, binary effects or inhomogeneous medium. And so there's lots of, I think it's a really rich field of interesting physics to study. And I think they will make different kind of double peak, different features that you can go study. And this is where the supernova community has missed out on a lot of it, in part because mostly when we run our supernova light curves, we do them in 1D. And so when you do a 1D, you go look at this, even kilonova, about 90% of the kilonova light curves out there for these neutron star mergers, so they're looking at the neutron star merger ejecta, about 90% of the work done there is done with a spherically symmetric explosion. So you don't capture a lot of this physics with a spherically symmetric explosion. You can do things where you do a toy thing where you add an energy source at the bottom and see how it affects the light curve and stuff like this. And we have that capability, but I think we're going to also need to include multi-dimensional effects. And there's a code developed at LANL for light curves. It's a 3D. It can do 3D light curves, and we're slowly adding the physics. But we can do now the kind of calculations that we were doing. I was doing we did very simply with this accretion luminosity. energy from the accretion, we can now implement in a much more detailed way with a full opacity Monte Carlo radiation transport calculation. The code is Supernova, developed by Ryan Walliger. So we now have, I think, better tools to get more accurate calculations. And I think we're going to find that we need to study all of the physics effects. So one of the things that I want to do is sit down with you all and just talk about, okay, what are different energy sources, and let's go try and model them, because I think there's a lot of stuff we could be doing.
Okay, thank you,
Right.
Chris.
Thank you. I have another question, but after Maria Joana, I ask if I can. Okay, thank you.
Okay, yes, we have Maria.
Yes, so I have a couple of questions regarding the Gamow mission. So if it is approved, what it is the policy for sharing the data, what it is the lifespan, and also if there was a study for comparing the capabilities for high redshift estimate of the GRB in comparison with the SVOM mission, and with the TCUS also is not yet approved. And if it is approved, will be launched in 2030 something. So I was just curious to see, since there are also other missions that have similar objectives.
Yeah, exactly. My guess is we'll be lucky if I'll be happy if any one mission gets approved. But there's a lot of these missions have some complementary properties, and so you asked when will the data get released. I think NASA is pushing toward, and I can't remember what we said we'd do in the proposal, but my impression is the data gets released quickly, if not immediately, because for these kinds of transients, I think if we don't get the data released right away, we could miss out on science. We need to coordinate with all the other missions up there. So I suspect there will be a strong push, and at least from my side, of we're gonna, when we find out whether we get, if we get past this first round, we're going to be talking to other groups that are proposing and saying, how do we coordinate with you, and how do we get the data out as quick as possible so that everyone could work together on these. I think that especially in this transient era, we're going to have to be releasing data immediately so that people can get the most out of the science. Most science out of the data. And that's, there's another, and so you've got me on one of my rants, and I would love your feedback on this. I just got done with a Chandra satellite review where there was, especially for neutron star mergers, there's like 5 proposals all wanting to do follow-up neutron gravitational wave events. And at some point, I think we're going to have to get the community to just say, we're going to do one mission. We're going to talk about what's the best cadence of getting observations, and all agree on it, and just get the observation and release it to everybody. Because the issue is that, everyone it was funny having a review committee decide which of these proposals was best. And the committee was deciding what's the best cadence. The committee are by nature not experts in the observations, because then they would not be on the committee, because they would have a
conflicting being the proposal.
Yeah,
yes, that's true.
And so
yes.
the worst thing you can do is have the committee decide what the best cadence is. It should be the experts, which are the people proposing, deciding the best cadence. But I will tell you, it didn't happen that way. So I'm actually going to argue for Chandra that they somehow coordinate everyone's, people put in proposals and then say, you're going to work together on this and get what you think is the best observations, because we won't have that many gravitational wave neutron star merger events. So we have to be fairly, we want to get the most out of every observation. But in the same with high redshift events, we're not going to get that many. We've got to, get the most out of them, because they're not as, we're not going to get 10 redshift 10 GRBs in the rest of my life.
Agree.
I mean,
it's very unlikely.
Yeah.
Yes.
So yeah, I think it's time for, we're going to have to figure out how we work together really well, and I think that's going to be a big topic in the next few years, because it's a big I care more now because I'm getting older, so I know that the number of events that I'm going to see is getting, there's a time frame of my lifetime that's going to get going to end. So I care about getting the most out of every event we have.
Okay.
Thank you. Yes, I have also a comment on that, because in many panels that I have been, sitting as a reviewer, or sometimes even, chair of the panel, I completely agree with you that there was sometimes, people that were belonging to, they were participating in multiple proposals that, of course, were competing. And, the proposal, I wouldn't say they were similar, but part of those could be merged. And I think this is a problem that I think we have, both as panel reviewers or in the committee, we have seen many times. But I still see that there is some hard time for people to, try to merge the effort. I feel that there is still some difficulty. I don't know if this is just my impression, or you share with me this opinion.
Can you comment?
Yeah, it's definitely difficult. So I think we just need to figure out. I think we can do better than what we're doing now. So we just need to figure out what we're doing. We need to work together to figure out a better plan. But it's a hard thing, and I don't know how to. And I care because somehow I got on the Chandra Users Committee board, and so this is my one chance to try to, at least for Chandra, change how Chandra does things. So I will be trying to get people to help me change Chandra at least, and then hopefully, if Chandra does a good job, other telescopes will also do a good job. So this will be thing that I'll go asking the community, how do we do this better? Because I think we need a better system.
Okay, thank you, Chris, for this answer. We have Rahim Moradi, and then I think Jorge has another comment.
Yes, thank you. Thank you for the nice talk. Regarding to this GRB you showed, is a long duration GRB regarding to T90, but it shows the kilonova. May I see the slide again?
Yeah, let me get them up. Hold on. Okay. All right.
So it's a long GRB, but it shows kilonova. So the progenitor, you said, can be considered like a binary, a neutron star or something like this.
Yeah, I mean, so you see this offset. So here would be,
this is,
here would be a potential host galaxy. I mean, I don't see any other host galaxy. So it looks like it's offset. So that implies to me that it got it somehow was kicked out and made out. And so, that's where you think maybe it's not a big massive star producing it, because, or if it did, it had to be somehow, it has to get further out.
Yes, this is interesting because we have studied this source and another one. Also, we sent the GCN. The title was a bit weird, but we said this is because we studied this and it was not fitting our BDHN model. So we predicted that the progenitor cannot be a regular for long GRB, so it should be from a merger from our study. Unfortunately, we only sent GCN for other one. I can share to you if I can share the screen, I can.
Yeah, let me stop sharing.
There were two GRBs. We sent the for this one. This is the GRB that you showed. Look, the afterglow. It is similar to the famous GRB that shows the kilonova, although it's long, but the afterglow doesn't follow the standard afterglow that we have found for the BDHN. Another one that I want to show you, we have sent a GCN, is this one, which we sorry, wrong. Okay, I don't know what's happening. This one. So this is another one, another long GRB that it shows the afterglow. It shows the similar behavior of short GRB. So for this one, we send the GCN that although it's a long, it has a long duration, it should show something similar to binary merger of neutron stars. So we have studied also more about this. We can, I think we can study more. This is interesting because we have predicted based on the BDHN model.
Okay.
But of course, it's not associated with a supernova.
Yes.
Yeah, and so one of the fun things, because the BDHN model has particular features in its supernova that I think we can differentiate from, say, this low nickel yield collapse star supernova that I ran, and so maybe it fits the data better. I mean, so this is the thing, is it may be that for we can do some studies and see how well we fit what we're seeing. So that would be really exciting.
I see. Yes. Really is exciting cases, because when we sent the GCN, we were not very sure about this statement, but now I saw this, I got excited. Okay, thank you.
Take all the data you can show us.
21, 12, 11.
Yes.
Let me check.
I asked you many times already.
Okay, thank you, Rahim. And I think Jorge wanted to make one comment on the discussion you had before. I don't know.
Well, also following on this kind of thing. So very actually very excited about this study. These studies pointing to the very early evolution and the signatures in the X-rays and optical and all on every associated emission in the early evolution of the supernova, possibly with the binary. And just I would like to inform Chris, we are actually writing a new code to follow the evolution of the neutron stars in full general relativity in such a way that we can also follow with a very detailed also the evolution, the interior evolution of the neutron stars in such a way that we can evaluate different the outcomes from different nuclear equation states, and also to evaluate possible transitions to different phases in the interior that can eventually be accompanied by releases of energy in these transitions that can also show particular effects also with the asymmetries of the supernova. So we are going to contact you as soon as we finish this new code to see if we can test it also with your new with the supernova explosions that you are the new two-dimensional models that you are running. We are finishing with also with Laura one of the studies also that you propose, and we are going to send you this shortly. The new studies about all the population, different kind of simulation, starting from different progenitors with different orbital period, all these starting and make a sort of a summary of all possible outcomes of the system. But we have, of course, we can generalize it to for the new models that you were speaking about. besides that, when coming to asymmetric explosions that are very important, we didn't do the analysis. We didn't do this analysis for asymmetric explosions, and I think we can do that. Also, because I would like to ask you specifically this, when we're going to the analysis of the kicks that you can get from this, and in a binary, especially in the binary system. So if you see any possibility in this system to get a kick out, and also to put the two stars, the two neutron stars, the one at the center of the supernova, the companion, in a possible collision in a few seconds after the supernova explosion. What do you think about that?
So you're thinking about having a kick that kicks. We have this close binary for this scenario, and then when you form, it's in the formation of the first neutron star, you want to kick it into the companion?
No, at the second
star.
In the second explosion.
Okay,
yes.
So I have a neutron star now, and I'm. Do I have a neutron star or a black hole? So I have one compact object, and then I want to kick the other one into the other compact object.
Oh yes, because you form the neutron star at the center of the supernova explosion, and maybe because of the asymmetries, and maybe I don't know, because in the interaction with the matter, as very much like in the common envelope phases, that you're going to have the merging of the two objects. Maybe also in these cases you can have some cases like that, when the two compact objects can merge in some of these.
Yeah, I think you could. I mean, the question is the question is how rare is that? Because the
yes, that's right.
Because it's a pretty it's a pretty small cross section for the kick to. So you will get a kick. The supernova, these asymmetric supernova explosions, we're not yet at where I think, like some of the people studying Thomas Young will say, yeah, we can explain the kicks that we see in the pulsar distribution. I'm not sure we're there, completely there yet, but we do know that these explosions are sufficiently asymmetric that the ejecta is going in one direction. It looks like the neutron star has to go in the other direction, and so these neutrons, the compact object will get a kick. Even black holes, if you have it where you're getting some mass ejecta when you form a black hole, so a black hole that's formed through fallback, the black hole will get a kick. So these neutron stars get a kick, but I think the chances of a neutron star hitting its neutron star companion or something like that, you can put it in a tight orbit where it'll merge quickly. The question is, can you get it in something where it merges almost immediately? That would be hard, I think. But we can look at the numbers.
Mm-hmm. Yes, it must be very rare.
Okay. Thank you for this.
Hello, can I have a question?
Comment? Yes, Shashank, please.
Friar, can you show the slide where is this correlation among the slide you saw? Where is the fluence and then duration? Can you just show that slide again? Yeah. So the one with the fluence and the minimal variability in time scale, what does it mean? Minimal variability time scale?
Yeah, I put this plot up, but I can't remember what Nora was calculating. So Nora Troja, this is her work, and so I'm not quite sure what her minimum variability time scale was. I think she was looking at the variability in the GRB, the gamma ray emission, and looking at what was this, how quick was the variability. But I'm not sure where. I didn't ask her how she got these numbers. And I can look back at the paper, but I must admit that I can't remember what she used to get these numbers.
Is something to do with the T90 or no?
I think it's more to do with she's looking at the variability in she's looking at how quickly does the emission vary, because a lot of some of these gamma ray, a lot of long gamma ray bursts have this nice, fairly slow variation in them compared to short bursts. So I think this is having to do with, it looks like there was a lot more variation in this, the gamma rays from this burst than a normal long burst. But I'm really speculating at this point because I need to go look at the details of the paper again on this.
Okay, thank you.
Good.
Okay. Yeah, I think there is no more questions, so I don't know if we should move to the conclusion of the afternoon session. Thanks a lot, Chris.
Thanks.
I see Johan Rafalski, if he could give us a message or something.
Hi, Remo.
Yes.
Thank you very much for welcoming me. What would you like me to do?
Just say hello from all of us, and that we are learning a lot about you.
Yeah, I of course admire the strength and width of the activity, and gamma ray bursts are obviously the one of the most misunderstood, I'm certain, and objects in the sky. So the research in that direction is very much aligning with my strong field interests. I am, however, not an expert. I listened a little bit to the lectures you invited me and saw very many nice ideas, but I'm not an expert. And I will hope one day I will learn from you.
Okay, don't worry, it will soon come. But in the meantime, bring our congratulations to the Academy in Budapest that nominate you a member there of the Academy. Our congratulations.
I'm very happy to be a member, and to, as a foreign member, I have, of course, no voting rights. Just it's like a honorary degree, but it came with a very nice diploma. I mean, it's not your usual thing, you know. It comes in superbly packed. I mean, I don't know how to get it out. Here we go, and
very nice, impressive.
Yeah, they know how to actually impress the world. It's a very, very venerable. I mean, they have one of the older European academies, and there's a seal, and it says nice things about in Latin. You can, of course, read Latin, and so you know, but that's what it is. So, and of course, there's a lot of interest in some of the aspects of the life of my fusion work, because they are working in this direction. So I'm helping them a little bit in that tabletop fusion.
Very good. And let's look for early physics in the sky.
Yeah, well, I, as you know, I'm more interested in cosmology. I leave the topic of astronomy to my son. It requires experiments, and I am a theorist. So cosmology is a good field to put my strength in. Knowledge of particle physics, nuclear physics, electromagnetism, strong fields, cosmology just next door to it.
Okay. Thank you again for your intervention.
Thank you. It's a pleasure.
Okay. With that, I think we can, Jorge, can we say something? We already spoke a lot. I would like to let you conclude, and I would like to thank everybody in Pescara, in Nice. We are making the connection more powerful in Nice, and we will able to use more often.
I have a small suggestion. Let's activate webcam and we make screenshot of the pictures of everyone, if you don't mind.
Yes, let's do that.
Please. It would be nice.
Yeah. Carlo, Laura, and Francesco, Yang Li, Wang Yu, put the camera on.
We are missing.
Delina, please, your camera on. Delina is a young student of mine.
Here she's we're missing still Laura, Sarah, Aditya, Alexander is here. Aditya,
Alexander is another student of mine. Alexander, please show yourself.
he's already here. Okay.
Wang Yu is missing. The secretary from Pescara.
Sare.
Wang Yu. What happened to Wang Yu?
He doesn't like pictures.
No, he just went out to bring something. I don't know what.
Okay, very good.
Well, we will keep Wang Yu for the next one. Okay. Maria, don't. No. Okay. Say hello to everyone.
Everyone, and thank you. Thank you for accompanying us in this in these 2 weeks. So it was long, but was very interesting, and we hope very much, and we look very much forward to meet you again, hopefully very soon.
And let's plan to see Chris early in the morning in the next connection. Let's send to him the latest paper and interact strongly. Okay. All my best.
Thank you very much.
Thank you, everyone.
Today,
See you next time.
of July,
Bye-bye.
is Bastille Day, and everything we should have a good thinking about the society become more sensible in the future. Okay.
Bye-bye.
Bye-bye. Thank you. Bye.
Bye, everyone.